Hi everyone. In this video, we're going to just briefly discuss the subject of the calculus of variations, which is the field of mathematics concerned with maximizing or minimizing the value of an integral functional. Now, most of you are probably familiar with maximizing and minimizing just a function, where you take the derivative of that function and set it equal to 0. But here we're trying to maximize or minimize the value of an integral functional, which is going to be slightly more complicated. And so what I'm talking about here is if we have some functional j, which is a function of the function x of t, where it's an integral functional. So we're integrating from some time, for instance, ta to tb, although it doesn't have to be time, it could be some other type of variable, of some function where this is a function of potentially x of t, the derivative, the time derivative of x, and then also t itself, and then where we're integrating over time here. So we're trying to figure out the function x of t. We're trying to find the function x of t that extremizes the integral of f, where here f is some function of x dot and t. We're trying to find the value or the function x that extremizes j. All right, so this is a fairly complicated problem that we're trying to answer here. And I'm not going to prove for you what the answer, how to do this, but I'll show you what's known as the Euler-Lagrange equation, which is a solution to this problem of how to find the function x of t, which extremizes j. But before I do that, I just wanted to sort of give you an idea of where calculus of variations is important in physics, because you could just look at this as simply a math problem. You're trying to do this extremizing math problem, but it turns out to be quite commonplace in physics, where it turns out that nature likes the extremum of things. So the solution to many physics problems is that you need to extremize some integral functional. So examples where it comes up, so maybe you've seen in optics, Fermat's principle, which tells us that light, the path that a ray of light will take, is the path of shortest time. Another place that it comes up is in general relativity. So the paths that particles follow in general relativity extremize what's known as the proper time along that path. And then in classical mechanics, so for us, it'll be important because in Lagrangian's formulation of classical mechanics, it turns out that the trajectories of particles, or trajectories really of systems, are given by the extremum of what's known as the action of that system. And we'll see more about that in future videos. So the general solution to this is given by what's known as the Euler-Lagrange equation. So if we take the time derivative of the partial derivative of this function f with respect to x dot, and then subtract the partial derivative of f with respect to x, and set that equal to 0, and then this is a differential equation ultimately that we can solve for x, then that function x, subject to whatever boundary conditions we might have, will be an extremum of j. So j, or a, will be the extremum. So something very important that I want to point out here is in these partial derivatives, you're going to treat x and x dot as though they are independent variables, which might sound strange, but So when you take the partial derivative and you hold everything fixed, in this first guy, you hold x fixed and take the derivative with respect to x dot. And then in the second term, you hold x dot fixed and take the derivative with respect to x. So you're treating x and x dot as though they are independent variables of our function f. And then the solution to this, again, will extremize the function j. So the last thing I wanted to do in this video is just give you an example of the types of problems that we use the Euler-Lagrange equation for. And specifically, I'll give you an example of geodesics in space. So these are spatial geodesics, which are simply the paths of shortest distance between 2 points. So for instance, in flat space, if we have some point A and B, and we want to find the path of shortest distance between 2 points, probably most of us already know the answer to this question, which is that it's just going to be a straight line. So this would be the geodesic. And you can imagine if we took any slight variation from that short line, any type of variation we might want, right? Any of these paths are going to be longer than the straight line distance. So we would say this black line is the geodesic, subject to the boundary conditions that it is a geodesic that starts at point A and ends at point B. Now in flat space, this problem, again, we've all seen it, but maybe we're in flat space and maybe there was some obstacle in the middle and then the path has to go around that obstacle. So then that would be a slightly less trivial problem. Or maybe we were on the surface of a sphere and we're trying to find the shortest distance between point A and point B on the surface of a sphere, which now this is a less obvious problem if you're constraining your path to be on the surface. Now it turns out that great spheres, are great circles on the surface of the sphere, which is to say circles that go all the way around. So parts of these great circles are the geodesics, but this to me would not be totally obvious. Like I wouldn't know, like, do you just try to, you could imagine drawing all sorts of different paths between these 2 points and it wouldn't be immediately obvious to me what the shortest path is. So the problem of finding the shortest distance, which is to say the problem of finding geodesics, is exactly the type of problem that we're trying to solve in the calculus of variations, where in these expressions above, the function j, right, j would be some function computing which gives us the total length of our geodesic, right? Our function here would be, we're integrating over a function which is probably parameterized by, say, x and y between these 2 points. And then that would tell us the shortest path between 2 points. So this is, again, just to give you an idea, a nice one, because this is just literally a physical path which you can visualize. But this is always going to be the type of problem that we're solving, except now it's not going to be a path in space that we can visualize, but for instance, a path through configuration space or something more abstract like that. So that's calculus of variations.